Hi, I'm Sim Larkin with the U.S. Forest Service Air Fire Research Team.
And I'm Karoline Barkjohn with US EPA's Office of Research and Development.
And we're here to talk to you about the AirNow Fire and Smoke Map, specifically the sensor data pilot that was done last year. This work represents the efforts of many people, not just us, but people in both the EPA and USFS, as well as at the University of Washington and Mazama Science, and we want to recognize their contributions. The Fire and Smoke Map sensor data pilot created a new fire and smoke map that was available on airnow.gov starting in the summer of 2020. And this map was done with the input of various users and was created with specific objectives in mind. This is what the map looked like on September 11, 2020, a period of particularly high air quality impacts. The objectives of this map are to try and provide enhanced air quality information during critical events where wildfires are producing lots of smoke. The other objective of this pilot is to include air quality measurements from low-cost sensors in a consistent manner such that they can be shown alongside permanent monitors. This work builds off of a partnership that the EPA and the U.S. Forest Service have had for a while. Specifically, the EPA AirNow system, which provides, of course, year-round 24/7 coverage and delivers real-time data on ozone and particulates, as well as forecasts for nearly 500 cities around the U.S., and really is designed to try and provide state-of-the-science information about air pollution for various stakeholders, including the public and the media. On the Forest Service side, this is a project that's being done under the auspices of the Interagency Wildland Fire Air Quality Response Program, which is a program that works with wildfire incidents across the country in order to create enhanced smoke monitoring, modeling, messaging, and interagency coordination during wildfire events. This program also produces trained smoke specialists, air resource advisors, that are dispatched out to those wildfire incidents. And those smoke specialists work with local communities as well as the incidents in order to produce various information needed by those communities. One of the products produced by those air resource advisors are smoke outlooks, basically forecasts, and other products related to transportation safety on an ongoing basis. The pilot was introduced in the summer of 2020, one of the worst air quality and smoke seasons on record, and received a lot of public attention. Generally speaking, the comments were very favorable and looked like it was filling a particular niche that was recognized by the public. The various data layers within the fire and smoke map include air quality observations, fire information, and also smoke plume extents. And these come from various sources. So with air quality observations, we're taking information from permanent monitors, temporary monitors, and low-cost sensors, in this case from the Purple Air network. We're taking fire information from ground-based systems related to the incidents themselves, as well as from satellite detections from a variety of systems. And for smoke plumes, we're tracking the smoke plume extent using those satellite imagery. If we look more closely at the air quality observations component of this, here the example map on the right is showing the period of the Napa and Sonoma fires in 2019 that produced a large amount of smoke. And you can see that if we just look at permanent monitors, while there is one monitor up in the Sonoma area that is reading very high, much of the rest of the permanent monitors are not picking up on the extent of this smoke at this point. There's not much better coverage afforded by the temporary monitors in this particular case, although in other fires, the temporary monitors do provide significant amounts of information. These temporary monitors are things like EBAMs that will be put out by various agencies to meet specific needs on a temporary basis, such as if they start seeing a lot of smoke in a particular area without any monitoring. However, when we add in the low-cost sensor data available from this region, we see a much better spatiotemporal picture of what's happening with smoke on the ground. So the low-cost sensor data here is shown as small squares, and you can see that it really fills out the picture of where that smoke is and just how bad it was during this period. Another thing that the map tries to do is it tries to bring that data down to the area where the user is located. So using the user's geolocation, we identify where the nearest monitors are and the nearest sensors are and bring those to the user's attention. So for example, this is an example from Florida now. If the user is located here, there were a number of fires at this time to the east that were producing smoke. Within this in your area system, we identify where the closest permanent monitors are, as well as where the closest low-cost sensors are, and try and make one-click access to all of that data. We also analyze the satellite detections, here coming from the NOAA hazard mapping system, and can identify where the nearest ones are, in this case 48 miles away to the east, as well as the fact that no large incidents through the incident command system have been reported at this time. So these fires were generally smaller fires. They didn't have that incident command system presence. Additionally, we can look at the smoke plume extents, and we can see that the smoke plume is about 28 miles away to the east as it moves slightly west, closer to the user. Additionally, with the geolocation of where that user is located, we can identify if that user is sitting in an area where a special smoke statement has been created. So these smoke statements are produced by those air resource advisors on the wildfire incidents. They're produced on a daily basis, and they include information about what's happening with the fire, what's happening with smoke in the region, and then forecasts for specific locations that might not have that capability otherwise. So should a user be in the location covered by one of these special statements, a banner will appear at the top notifying them. We will also notify them within that in your area sidebar. And with one click, you can get access to the full smoke outlook issued. So within that, you can gain access to specific forecasts for specific locations. There were many data considerations and challenges that we faced during the creation of this map, and I think that they're indicative of trying to bring together low-cost sensors and permanent and temporary monitors within any sort of hybrid system. So timeliness is a big issue. The different monitors and sensors have very different lag times before the data becomes available. In general, low-cost sensors are available very quickly. They're piggybacking off of their users' Wi-Fi systems, and they arrive within an accessible point very quickly. They're also producing very short time averages, as we'll talk about in just a second, which allows them to report quickly. Permanent monitors can report back in a variety of ways, but generally have a little bit longer lag, and of course are trying to do hour-long averages, which delays their return a bit. And temporary monitors can be reporting back through satellite systems that can have significant delays before reporting back, or report back in bursts. Another issue was this time averaging. There's a trade-off that you have to identify and figure out where you want to be on between displaying rapidly changing shorter time averages, such as those available from low-cost sensors, and having longer time averages that are more indicative of what has been associated with health effects. And so time averaging length for what you want to display was a particular choice we had to make in the development of this map. Now, low-cost sensors can report back, particularly purple arrows report back, every couple of minutes on a sub-hourly basis. We have the permanent monitors and the temporary monitors reporting back on sort of an hourly basis. And of course, at the other end of the spectrum, we have the daily air quality index values. We chose to go with the nowcast AQI values, nowcast being a multi-hour averaging system with a spectral frequency of about 3 hours. So it's somewhere in the middle, but it does not tap in fully into the capability of the low-cost sensors for that sub-hourly reporting, while retaining a bit of a better link to the longer-term health averages. Another issue that we had to face was consistency. The low-cost sensors are a lot more likely to have various kinds of issues, including being turned off from day to day, or even having their situation seem to change. We saw several cases where low-cost sensors appeared to be moved inside at certain points. And there can be other issues just with the technology itself. This makes for an enhanced need for quality assurance and correction of those type of sensors, as we'll talk about later in this talk. As I said, we had many choices in making the map. We stuck with the nowcast AQI level, and in doing so, we were able to use the air quality index color scale, which is the standard one that many of you will be familiar with. We also used gray to indicate missing data. Another choice we had to make was what was the symbology of the air quality observations going to be. We decided to stick with circles for permanent monitors and identify temporary monitors with a similarly sized triangle. Those temporary monitors can have potentially some additional issues. Also, we wanted people to be able to recognize that they were temporary and that they might go away later. On the low-cost sensor side, we used a smaller square to try and indicate the sort of relative uncertainty value of the low-cost sensor data. And also because there are so many more of them that you could get sort of fields of these little squares to fill in a color block. There are, of course, many pluses and minuses to both types of equipment. You have the higher quality, professionally sited, professionally maintained permanent monitors and temporary monitors, typically because they're typically put out by agency personnel. They are, of course, higher cost, limited number, and they can be slow to report. On the low-cost sensor side, the low cost means that there are many times the number of permanent sites available, and because they're typically placed in locations with Wi-Fi access, they report back very quickly. But you do lose control over siting, maintenance, and this enhances that need for data quality assurance and quality control. And with that, I'm going to turn it over to Karoline.
Thanks, Tim. Now I'll talk us through the steps that we're using to quality assure the data that's showing up on the air sensor data pilot. So we have a number of projects that enabled this work. We have secondary data that was provided by a number of state, local, and tribal agencies where they had purple airs co-located at their air monitoring sites in order to understand their performance in their specific location. We also had purple airs that we sent out as part of a sensor evaluation project, the long-term performance project, to capture a variety of conditions across the country. And lastly, a smoke impacted project looking at specifically co-locating purple airs with monitors during smoke impacted times. And so from those data sets, we built a correction based on the 24-hour averaged data, and then we tested it based on 1 hour ambient and smoke impacted validation data sets. And that allowed us to have the confidence in order to display this data on the pilot project. Next slide, please. And so now I'm going to walk you through the steps to display the purple air data on the pilot. So first of all, when you register your sensor on purpleair.com, you can decide whether you can select whether it's an indoor or outdoor sensor. So we're only pulling in the outdoor sensors for this project. Then we're averaging the purple air PM 2.5 and relative humidity data to 1 hour. And as you'll see in a couple slides, we're using that relative humidity data in order to correct the PM 2.5 data from the sensors. And then we're removing data when the channels differ. So you can see in the bottom right here a picture of a purple air sensor with the two Plantower PMS 5003 sensors underneath those two blue rectangles. And those are the A and B channels. And so on the plot here, you see we're plotting channel A versus channel B. And in black are the points that are included, and in red are the points that are excluded. And so we're excluding points when they're different by both 5 micrograms and 70%. And 5 micrograms is important because you might have a low absolute difference at a low concentration. That would be a high percent. So for example, 1 microgram plus or minus 1 microgram, is 100% difference. But those two measurements are pretty similar. And then at the high end is when that 70% is important. And so 70% is really compromised. It's removing these worst offending points in red, but it's leaving in some questionable points that you see in black. But we're really doing that. That was the decision we made in order to increase data availability. So you can imagine if one sensor is correct and the other sensor is 70% incorrect, when you average them together, you're going to be within 35% of the correct point. And that data could be very valuable if you're one of those sensors that is in a secluded spot on the map where there aren't a lot of other measurements. Next slide, please. And so from there, we're averaging the A and B channels. If the relative humidity is outside of 0 to 100%, we remove it. So occasionally the relative humidity sensors will throw out something like 200%, which we know isn't physical. And then we're going to replace that relative humidity with 50% if it's missing or if we remove it. And then we're going to apply the US-wide correction, which you can see in the bottom right. And so on the plot here, I'm showing you the 1 hour federal equivalent or near federal equivalent methods. So those are the stationary and temporary monitors that Sim showed during his section versus the 1 hour purple air. And so in orange, you see the raw data that would be shown on purpleair.com. And then in teal, you see the US correction that is closer to that 1-to-1 slide, 1-to-1 line. Next slide, please. And then, as Sim said, we are calculating the nowcast AQI to categorize it into those 6 AQI categories at a higher time resolution than our traditional 24-hour AQI, which is really balancing our need for real-time data, the measurement uncertainty in both the sensor and also even the federal equivalent methods. We know that there's some noise at those hour averages, and then also the uncertainty and health effects that Sim mentioned. Next slide, please. So for our next steps, originally during our first evaluation, we really saw PM concentrations up to about 200, 250 micrograms. But unfortunately, last year during the 2020 wildfires, we saw very high concentrations out west. And so some of our data shows concentrations up to 1,500 micrograms. And the purple air sensors have a nonlinear relationship at higher concentration. And so we're fitting a nonlinear fit that will be implemented on the fire and smoke map, hopefully in advance of next fire season. Next slide. And so if you'd like to learn more about this project and some of EPA's other work with air sensors, you can go to the Air Sensor Toolbox, where you'll find some webinars, presentations, and other resources. If you want to check out the AirNow Fire and Smoke map, you can go to fire.airnow.gov. And we also have a few publications. So Amara Holder's paper, evaluating sensors during wildfire smokes impacts. And we also have a discussion paper in atmospheric measurement techniques where we built the original correction and we're preparing an additional manuscript on this higher concentration correction. Next slide, please. So thank you all so much for tuning in. We look forward to answering any questions during the Q&A, and you can also feel free to follow up with us via email.
Thank you.